Okay. So let's get started. Thank you for joining this session of the virtual seminars in economic theory. Today we have Tilman Börgers from the University of Michigan, who is going to present similarity-based learning and similarity equilibria. It is a joint work with George Mailath. The format of these seminars is as follows. We have a 60-minute presentation with time for entering questions from as people in the panel. And it's going to be followed by a 15-minute session for discussions and questions and additional questions. We request all attendees to keep microphones muted during the talk. However, if you have any question, please post the comment or question in the chat. We will try to read your questions to the speaker. There will be another opportunity to ask questions live in the Q&A session at the end of the talk. This talk is going to be recorded. Before I hand over to Tilman, let me remind you that these seminars take place every Thursday at 4 p.m. UK time. And next week we have with us Inga Adeyman from University of Arizona, who will present authority in a theory of the firm. And our guest panelists will be Wouter Desen and Dimitri Migrov. As usual, you can find more information about the coming list of speakers on our website or by following us on Twitter. Thank you, Tilman. The screen is yours.
The screen is very good. Thank you very much for having me, and thank you to all the organizers for organizing this seminar. This seems very good, and I should attend it more often. I really miss in this format the opportunity to also sort of get to know the research of other people. So I looked up the research of the organizers before I came to read, just to see what you, and there was so much interesting stuff that I would have liked to hear about. So I'm sorry that there's no chance to do that. So this is joint work with George Mailath, and it's still preliminary, so we don't have a paper to circulate, and it's embarrassingly long that we don't have a paper to circulate, but for some reason the crisis has at least given everyone the feeling that they are more busy, and I don't quite know how that happened, but we are incredibly busy with lots of stuff, and so we don't get to write the complete paper. So what does the paper do? So the paper takes the point of view that equilibria in games come about through learning, not by themselves, but that players have to play a game repeatedly, gain experience, sort of act in a sort of boundedly rational way as they learn. And if the learning converges, it converges maybe, hopefully, to Nash equilibrium, at least in some class of learning processes. So we interpret equilibria as the outcome of a learning process. And initially, we simply wanted to ask ourselves, but how about games of incomplete information? How should we think about this process? So, and in particular, the following question was on our mind. There are many games in which that we study sort of in the applied literature on games of incomplete information, in which the type space or the signal space that is large. So even say take an auction. So often we write auctions models in which players have a continuum of types. And now if we want to think of the players as learning how to play that game through repeated play, then maybe the most naive and simplest idea is that just sort of there are many periods, and in each period a player is again assigned a type, so maybe a valuation in an auction. And so players learn repeatedly because from time to time they are assigned the same type. And then, but that story seems a little difficult because, say, if types follow a continuous distribution, the probability is 0 that you have again the same type in some further future period. So that seems to me to reflect the general life experience that no situation is exactly the same as any previous situation in which I have been. And so As a consequence, if we want to learn how to behave in games of incomplete information with large type spaces, we presumably have to learn from similar periods in the past, not exactly the same, but similar experiences in the past when we had a similar type. And so the idea was, and the idea is to ask which effect this has on equilibrium outcomes that we have to learn by extrapolating from similar experiences in the past. So here are some bullet points that say the same thing as I just said. So equilibrium play comes about through repeated play and adaptive learning. That's the perspective through which we are going to look at equilibria. So presumably we are exposed to signals that define our types, and we have to learn from being sort of in the same situation or in similar situations over time. So what this paper does is we propose an equilibrium concept for games in which players regard some signals as similar to other signals. So we take an exogenous notion of similarity that players use to interpret their experience, and we ask, given that notion of similarity, how would we define equilibrium? So we propose an equilibrium notion. And then we study the connection between this equilibrium notion and classical notions of equilibrium in game theory. That's one part of the paper. And the other part of the paper is to write an explicit learning model in which the learning takes place over time, and we model the dynamics of learning. And we want to use that for two purposes. One is to provide underpinnings for our equilibrium notion. That is, we want to prove theorems of the sort that if this learning process converges, it will converge to an equilibrium. We call them similarity equilibria. So first thing is we look for theorems of the sort. If learning converges, it will converge to similarity equilibria. And then we are also going to use the explicit model of learning to ask ourselves the question whether there is an equilibrium selection effect. So whether if equilibria are reached, some equilibria are more likely to be reached than others. And we obtain a small result along those lines. This is the agenda. This is a broad agenda, and you will see, like with all, with many papers, that the first slides of the introduction raise more hopes than the rest of the talk will ever satisfy. So that's lower expectations right away rather than keep expecting. I don't know whether you have high expectations, who knows, maybe they are already lowered. So that was sort of the thought with which we started. But then in this paper, we will take a particular subcase of this. And the main characteristic of this subcase is that it's actually not games of incomplete information, it's a game of complete information. And people get payoff irrelevant signals. So people are just sort of, we play games, sort of we participate in strategic interactions. There's lots of sort of observations that surround us. We have to figure out, are those observations in any case relevant to in any way relevant to the game that we're going to play? They are payoff irrelevant, but they could of course be relevant in the sense that they might allow us to predict other people's behavior better. So other people's behavior might be correlated with what we're seeing. And so instead of writing a model in which players' types are payoff relevant, we just write a model in which players live in an environment that exposes them to constant noise and constant sort of large set of signals, and players know the game that they're going to play, but they have to figure out whether this information allows them to predict other players' behavior. So that's the first strong limitation of what we're going to show you. So as I have already said, similarity notions will be exogenous here. And it's obvious that you will also might want to study how players adjust their similarity concepts as they learn. But in this paper, we will not do this. The emphasis on the paper will be, at least in parts, on the following question. The question will be, is similarity transitive or is it non-transitive? So, and we will allow similarity to be non-transitive. So the idea is that 0 is similar to 0.01 and 0.01 is similar to 0.02, so that you might have a sequence of things where each thing looks similar to the next thing, but the first thing doesn't look at all similar to the last of those things. And so we will allow similarity to be non-transitive. And the second is we will also allow it to be non-symmetric. So we will allow for the possibility that an object X is similar to Y, but Y is not similar to X. And that at first sight might look a little bit counterintuitive, but I think it looks counterintuitive because I'm using the language of similarity. But there is another way of thinking of our model in which lack of symmetry makes more sense. And this alternative interpretation is I encounter a situation, I think about, have I encountered similar situations in the past? And some situation pops up in my memory, so to speak, and says, oh, this was a similar situation. And this effect of what situation triggers which memory, that doesn't have to be symmetric. So the way I like to illustrate this is that when I walk the streets, I see other people walk their dogs. I see how those dogs behave, and I see, oh, I recognize that style of behavior. My dog does the same. So every dog that I see in the street reminds me of my dog. But then when I'm at home with my dog, that my dog does not remind me of every other dog. Once I see my dog, I only think of my dog. So so the generalization of that is this relation of one experience triggering the memory of another experience might not be symmetric. So we allow it to be non-transitive, the similarity relation. We allow it to be non-symmetric. Of course, we will look at the special case. What if it is transitive? What if it is symmetric? And what we find is what are the main results again? So now I've told you a little bit about the limitations of the paper. So I told you the first thing we are going to do is we are going to define a concept of similarity equilibrium and relate it to classical equilibrium notions. Now that I've told you it's a game of complete information, what would be the relevant classical equilibrium notion? It would be correlated equilibrium. These players live sort of in a noisy environment where what I see might be related to, correlated with what you see. We might sort of evolve so that we condition on correlated observations, and then we would play a correlated equilibrium. So we're going to ask, is our equilibrium notion the same as correlated equilibrium? And if similarity is symmetric and transitive, then the answer is yes, subject to small qualification. That I do not mention in this point yet. But if similarity is non-symmetric or non-transitive, then the equilibrium notion differs from correlated equilibrium and from, as far as I can see, any standard equilibrium notion for games. Then our second ambition was to write down a explicit learning process that describes how players learn from similarity and to study the properties of this learning process. And the result that we aim for and that we also obtain is a result that provides underpinnings for our notion of similarity equilibrium. So a result that says if similarity-based learning converges, it converges to similarity equilibrium. We will prove not prove, but state two versions of this result. And then the third question was whether there is some equilibrium selection effect. Once we have our explicit model of learning, suppose we keep track of learning over time, we look at its convergence properties, does it favor some equilibria over others? And we construct one particular case in which similarity-based learning actually ends up in an equilibrium in which players ignore all the signals that they get. Over time, they come to the conclusion that none of it is relevant for predicting what the other players do. And so in other words, in that case, they will learn over time a pure strategy Nash equilibrium of the game, and they will give up on any attempt, so to speak, from the outsiders, but from the game theorist's point of view, they give up on correlated equilibria. So in particular, so if I look at classes of games that have particularly attractive correlated equilibria, so we go back to one of Aumann's 1974 examples, and we construct in that example a model of learning for which we then show that learning actually will lead players to completely ignore all signals. The reason we are interested in that result is in part that we wanted to know whether similarity-based learning favors simple equilibria. So the question was, for example, suppose you have a game in, so going back to games of incomplete information, which is what we sort of originally thought about. Suppose you have a game in which sort of fine details of very higher order beliefs matter. So we were wondering whether equilibria of that sort, say like the equilibrium of the most basic global game, whether those equilibria can be learned if players have to learn based on similarity. So we have not realized our ambition to study games of incomplete information in full generality, but for a small class of 2x2 games, we can prove that players actually completely ignore signals if the signals are payoff irrelevant, and therefore fail to learn possibly more attractive correlated equilibria. Maybe I do 2 more slides, and then I will interrupt for a moment to see whether there are any questions. One slide is that is on related literature. I'm pretty sure this slide is incomplete from what I hear, but let me just say the first thing is that our paper is clearly related to case-based decision-making in the style of Gilboa and Schmeitler. If I understand this correctly, then the difference is that our model is more primitive. Our model is naive in the sense that similarity is a binary relation. Either one thing is similar to another thing or it's not. Whereas in Gilboa and Schmeitler, similarity is a gradual relation. You can be more or less similar. So we do this sort of course, for simplicity. It's not that we think similarity is by its nature a binary relation. In our setting, it's the binary relation that allows us then, or takes us to focus on issues like transitivity and symmetry. And I think the same issues would also show up to some extent in if we return to the Gilboa-Schmeitler model of a more sort of graduated similarity, and we could study the implications there too. But so in a sense, we give ourselves a more primitive model to work with. There is some literature that applies Gilboa-Schmeitler to games, and our last result on equilibrium selection is quite closely related to Steiner and Stewart, I think, who take actually the Gilboa-Schmeitler model to some version of global games. And there's also a paper by Itzhak Gilboa and Rosella Argenziano on similarity-based equilibria. So those papers are related. I think there is no direct overlap in the sense that we do exactly the same. But clearly that's a closely related literature, as is the work that Philip Giel has been doing for a long time on analogy-based equilibrium. Now, in those papers by Philippe, I think the analogy is partition-based, which means that it's transitive and symmetric. So in our case, if our similarity relation was transitive and symmetric, then it would correspond to a partitioning of the type space. So in that sense, we have a more general model than Philippe has and explore the consequences of that more higher generality. Unlike a traditional introduction, one more slide to the introduction. Right away, future work. So this is just again to promise that at some point, hopefully, we will return to the case when signals are payoff relevant. And then, in a sense, a model as we construct is aimed at asking the question. So the signals that players receive can be interpreted as their types a la Hasiani, and therefore, in principle, there is a corresponding infinite hierarchy of beliefs about what other types the other players have. And in principle, a model like the one that we show models players who do not explicitly think in infinite hierarchies of beliefs, but who act as if they had them. So one thing in which I'm interested in is that it's this interpretation of the theory of gains of incomplete information that, like utility maximization, it's not necessarily something that you do explicitly, that you take derivatives and determine your consumption. I tend to never do that. And it's the same with infinite hierarchies of beliefs. You behave as if you had them. That is the story that we want to tell. And then we want to ask, can it be that equilibria depend in complicated ways on higher order beliefs? Can those equilibria be learned? The next slide is the grandiose roadmap, which says I define similarity equilibrium. I discuss its relation with correlated equilibria. Those are the first two sections. And then after that, I introduce the learning model that provides the underpinnings for the equilibrium notion and study its asymptotic behavior. Now is a moment when I could pause and ask whether there are any questions. Uncle, what's the conclusion? I should continue? Very good. Now, one further disappointment I cannot save you from is there will be only two players. It gets more and more special. Soon there will be only one action per player, then the talk will collapse at that point and we will all go home. No, there are two players, but we are at home, so we don't have to go home. So there will be two players, that's just for simplicity. Each player has a finite set of actions. Everything will be finite, that's to avoid just complicated math. It's a complete information game, so players have utility functions that only depend on their action profile and not on their types. But as I said, players get signals. These signals are payoff irrelevant. The signal that player I receives will be denoted by theta I, and there will be a finite set of possible signals. And there will be a sort of objective, a common prior, a distribution over these signals. And in principle, later we will have in mind that sort of the game is played, when the game is played repeatedly, then signal realizations are independent across periods. But signal realizations are, of course, potentially correlated within period. So if can involve correlations, and we assume that F has strictly positive marginals, because if there were a signal realization with zero marginal probability, we could just drop it from the model. And similarity will be modeled simply by a similarity correspondence. As I said, it's a binary relation. So with every signal theta I, we will attach a set Si of theta I of signal realizations that are similar to theta I. This is player I's perception of similarity. So Si is a correspondence, so a function that maps the set theta I into the power set of the set capital theta I, and that is not allowed to map into the empty set. So Si of theta I is a subset of signal realizations, namely those signal realizations that the decision maker, the player I, regards as similar to signal realization theta I. We will assume, a grandiose assumption here, that this, so this is like a binary relation. We will assume that it's, so I'm using the language that we use typically for binary relations. I'm going to assume that it's reflexive, that so that things are similar to themselves. So, but the two other properties that I discussed, symmetry and transitivity, will not be necessarily assumed. So we will define them here, and then we will sometimes study their implications. So symmetry means that if theta I hat is similar to theta I, then theta I is similar to theta I hat. And transitivity means that if theta I hat is similar to theta I and theta I tilde is similar to theta I hat, then theta I tilde is similar to theta I. And those properties will not be assumed, but we will refer to them from time to time.
Tilman?
Yes.
Question from Santiago Oliveros. He's asking, does the number of signals and the number of actions matter?
Not for the results that I'm about to present, not per se. That's what I can say about that. There will not be any assumption in any result on that. Questions, can I imagine questions for which it matters? And that's too complicated for me to think about at the moment. So, so there's no assumption on that. So, a strategy of a player maps the signal that the player gets into the player's action set. So notice from this that our model does not say that you cannot distinguish between similar things. You can't even tell the difference. And therefore, you would have to choose the same action in two similar situations. It just says this situation is similar to another. You perceive it correctly. You can condition your act on what is the exact situation that you perceive. And your choice is influenced by other situations that you regard as similar. So it's not a model of fuzzy perception. It's just a model of what do you regard as relevant to the current situation in which you are. And then I can say, give you the definition of similarity equilibrium. So it just says that for each signal, the action that you take has to be utility maximizing, given your perception of which actions is the other player going to take, conditional on the signal that you have received. But not conditioning on that signal, but conditioning on that signal or similar signals. So this is the conditional expected utility, except that conditional probabilities tend to be a numerator and a denominator, and I have left out the denominator because for maximizing expected utility, the denominator does not make a big difference, no difference actually. So this is your expected utility conditional on the signal, on the set of signals that is similar to the signal that you have received. So it's an equilibrium notion. You correctly perceive the other player's actions. This is the true distribution of signals. And you take a sum over all signals that are similar to the one that you have just seen. There we have arrived at the equilibrium notion, not very difficult. And sort of the natural thing that maybe natural thing that you would come up with. My objective is to relate this in a first step to correlated equilibrium. And I will use the interpretation of correlated equilibrium and the reduced form definition of correlated equilibrium. A correlated equilibrium is simply a distribution over the profiles of actions. And therefore, in order to relate my concept of similarity equilibrium to correlated equilibrium, I have to derive from correlated equilibrium the implied distribution of actions. So given any strategy profile, you can calculate by putting, sort of combining the strategies with the distribution of signals. You can calculate for any profile of actions of player 1 and 2, how often are they going to be played. And if the signals are correlated, of course, this is potentially also a correlated distribution of action profiles. So the question will be, give me a pair of strategies that form a similarity equilibrium. Does it follow that the implied distribution over actions is a correlated equilibrium? This is the first question that we ask. And the answer is, so if you first read the proposition, you could read this slide in reverse order. The proposition says if, and forget about the first sentence, if both players' similarity correspondences are symmetric and transitive, then the action distribution implied by a similarity equilibrium is a correlated equilibrium. So this is a sufficient condition for the action distribution to be a correlated equilibrium, but we need an additional assumption. And the additional assumption we think is generically satisfied, where genericity would be over utility functions or also over distributions over signals. But
we have two questions that perhaps you want to address.
Mm-hmm.
So the first question from Spiros Galanis is, could we interpret this as an agent who is unaware of some signals? So from the perspective of the modeler, it is as if he lumps them together.
So, so note, record that I want the agent to exactly perceive the situation as it is. So my sense is, so he doesn't lump them together in the sense that he responds to different situations that are similar to each other necessarily in the same way. So in a sense, he has to be aware of the difference between these situations. So I think it's a little different from unawareness, if I interpret this right.
Yeah, and another similar question is, can we, from Difeng, can we think similarity between agents receive signals and other signals as the agents receive signal plus some error or noise? For instance, even if I receive theta, I may think this perception of this reception is wrong and the true one should be theta prime.
Right. So again, so so maybe you can think of it like that. I'm not sure. So I mean, and so in principle, sort of a classical model of you get a signal, but maybe the signal is noisy would not have this binary relation here. It would have a more quantitative relation. So I am not sure if I'm allowed to say this. Okay, so for our theorem on correlated equilibrium, let me go back to that. What we have an additional assumption which says sort of, which we think is generically satisfied, which says that whatever strategy the other players play, if it's a pure strategy, whatever signal you get, your expected utility maximizer is unique if you follow this similarity-based style of thinking. And it's only with this assumption that we can prove this grandiose proposition. With this assumption, I think this grandiose proposition is really relatively trivial because the transitivity and symmetry means that the similarity notion can be represented by a partition. The unique best response assumption means that conditional on which element of a partition you observe, you have to choose the same strategy conditional on the elements of that partition, and therefore it turns sort of into a model in which the partitions could just as well represent your information. And then this is just a model in which players sort of, it's the model in which Aumann originally formulated correlated equilibrium, and the statement that that's equivalent to the action, to the reduced form formulation of correlated equilibrium that I took as its definition. That statement is just a standard statement about correlated equilibrium. What follows next is a long sequence of examples in which we show similarity equilibria in cases in which the assumptions of the previous proposition are violated. And these examples then show sort of mistakes, in a sense, players make if they have a similarity. So in some sense, one could regard these as mistakes. So some of these examples have a flavor of, they display behavior that has a flavor of sort of behavioral game theory. So here's an example. So given the shortness of time, I'm not sure that I will go through each of these examples in detail. Let me try. Here's an example. The game on the left-hand side is a two-player game, and I think it even lacks a pure strategy Nash equilibrium. Of course, our players in principle could play mixed strategy equilibria if they receive the right signals. But we're going to say here these players receive perfectly correlated signals. So our model in particular includes the case that we would call a public signal. So the signals for the two players are perfectly correlated. This is what this distribution on the right-hand side says. Each player gets 1 out of 3 signals, and there is only positive probability on the diagonal, and each realization is equally likely as every other, but players interpret these differently. So player 1 regards each signal as similar to no other. So player 1 regards each signal as unique, whereas player 2 regards each signal as similar to its nearest neighbors. The signal on the left has only 1 nearest neighbor, the signal in the middle has 2 nearest neighbors, and the signal on the right has only 1 nearest neighbor. So the player 2 has the nearest neighbor idea of similarity. Player 1 has the sort of things, nothing is similar to anything else. This game then has the following similarity equilibrium. Both players play the same strategy. They play conditional on signals 1 and 3, strategy A, and conditional on signal 2, they play strategy B. And so let me just show you why this is similarity equilibrium. For player 1, it's obvious that it's a similarity equilibrium because he notices the state exactly, and he doesn't think it's similar to anything else. And moreover, his utility function is such that he wants to match the other player's actions, and that is what he achieves in this equilibrium. So he will always exactly play the same action as the other player. It's different from player 2. He doesn't actually have any interest in that at all. So if player 2 sees signal realization 1, he thinks, oh, that's similar to signal realization 2. So let me think about what player 1 does when I saw signal realization 1 or signal realization 2, because signals are perfectly correlated. In 1/2 of those cases, player 1 played A, but in the middle row, he plays B. So in 1/2 cases, he played A. In 1/2 of the cases, he played B. And so I am going to ask, what's my expected utility maximizing strategy? Is it A, which gives me 1/2 times 0 plus 1/2 times 3? Or is it B, which gives me 1/2 times 2 plus 1/2 times 0? And so I come to the conclusion it's A. Of course, if I hadn't had the similarity notion, I would have wanted to play B. But the similarity notion leads this player to play A. In the same as in the right column. So if he sees this third signal, if he sees the middle signal, suddenly he thinks, oh, all past experiences are relevant to what's going on here. And therefore, I think with probability 2/3, player 1 is going to play A. With probability 1/3, he's going to play B. And therefore, my expected utility from playing A is 1, but my expected utility from playing B is 4/3. And so in the middle realization, it's optimal for him to play B. So this player ends up, because of his similarity notion, to exactly match the other player's actions, which is the opposite of what he wants. The implied action distribution is this distribution here, that 2/3 of the time they both play A and 1/3 of the time they both play B. And of course, that is not a correlated equilibrium. then I have an example in which the similarity notion is transitive but not symmetric. Again, there is a two-player game. Both players receive a signal. The signals are perfectly correlated, and there are only two realizations per signal. And player one thinks each signal is unique. There's nothing that is similar to anything else. Player two has this similarity notion. He thinks the left signal, signal one, is unique, but signal two is similar to signal one. So that's a case of a non-symmetric similarity relation. And it leads to this equilibrium here. So I'm playing, again, both players playing the same strategy. I'm playing A when they see signal 1 and B when they see signal 2 is an equilibrium. Clearly, this is an equilibrium for player 1 because he wants to match player 2's actions if player 2 plays A or B. It's an equilibrium for player 2 if he sees theta 1, 2. He thinks only this is a unique signal, nothing is similar to it. It's perfectly correlated with theta 1, 1. He saw player 1 in the past always playing A. Therefore, his best response is also to play A. That's good. If he sees theta 2, 2, he thinks, oh, that's similar to everything that's happened to me in the past. Therefore, he thinks player 1 is going to play A or B with equal probability. And therefore, strategies A and C give him utility minus 0.5 in expected terms, whereas the middle strategy gives 0, and therefore he plays the middle strategy. But if he didn't have this confusion about similarity, he would realize that actually conditional on signal 2, he should play C. But he doesn't dare so because he thinks it's sort of similar to signal 1. And so again, the implied action distribution is not a correlated equilibrium. Player 2 should deviate when he plays B. The third example is finally a familiar game. This is to illustrate the reason why we need the uniqueness assumption. The familiar game is matching pennies. Again, the signal distribution is completely correlated signals. The similarity is that now both players think, oh, everything is sort of similar. I don't see any difference between these signals. And then, of course, because we are not saying that conditional on what you see as similar, you have to play the same action. This does allow players to condition and to play conditional on one signal. Here, the signal realizations are just theta I and theta I hat, conditional on one signal head and on the other signal tails. And so if they do that, they end up completely correlated, which is not exactly what player 2 really aims for. Notice here, the reason this is possible is that conditional on this partition players are indifferent between head and tails. But we are not saying that they cannot perceive the difference between the signals. So that if they resolve this indifference in an unfortunate way, they could create this complete correlation of their choices, which is not a correlated equilibrium. Here, one could say this has the flavor of correlation neglect. Players look back at the past and they don't notice the complete correlation of the other player's actions with their own. Player 2 should notice that. It would do him good. This is the end of the discussion on similarity-based equilibrium and correlated equilibrium. Just pause for a moment. And
there is another question from Santiago Olivero, so perhaps a good moment to read it.
Mm-hmm.
I may be mistaken, but in the intro, symmetry and reciprocity were sufficient conditions for equivalence between the equilibrium notions, but now the arguments are about necessity. Are symmetry and reciprocity necessary and sufficient for equivalence of similarity, equilibrium, and correlated?
Okay, so the structure here was only that I said there are sufficient conditions, and then I showed counterexamples that said if I violate one of them, I can find a counterexample. Of course, this does not say that there would not be a relaxation of the assumptions. And in a sense, it cannot be that they are, the assumptions are No, it cannot be that the assumptions are necessary and sufficient. We can take a game in which players have strictly dominant strategies. They will always play, I mean, even if they have the strangest similarity relations, they will play their dominant strategies. So in games with strictly dominant strategies, similarity equilibrium would be the same as Nash equilibrium. It's another sufficient condition. It doesn't rely on any properties of the similarity notion. All right, so then let me next introduce the learning model. The learning model is also not, I cannot say that it's very subtle. There are time periods, discrete time. The signals that players play repeatedly in the game, that is underlying, in every time period, they receive a signal before playing the game. Player 1 receives signal theta 1t, player 2 receives signal theta 2t. The signals are independent across time, and they are distributed according to f. So this is a scenario that should make learning easy. So I mean, there are of course many other things that stay in the way of learning how to play an incomplete information game. In particular, this independence is not likely to be a very realistic assumption, but we granted ourselves here. We write A1t and A2t for the actions that players 1 and 2 take in period t. The history of length t just describes for every period which signal did player 1 receive and which action did he take. Which signal did player 2 receive and which action did he take. Of course, each player observes only their own signal, their own action, and the other player's action, but not the other player's signal. Of course, maybe of course, so I should say that. So that's what we have in mind. Oh, there it says here, players observe both players' actions and their own signal. Great. And players will, in each period, look back, and when they choose what to do, they will learn adaptively. So this is a little bit, say, the model that we have in mind is, say, fictitious play. You look back, you look at the signal that you get, you think, oh, and what did I do in not what did I do, what did the other player do in the past, in periods in which I got this signal or a similar signal. And they optimize against the empirical distribution of the other player's actions. Now, in order to start off that process, I have to begin with a sufficiently rich initial history, so that in the first period in which my learning process really starts, when players look back, they see enough sort of relevant observations. And this assumption here says that there is at least one relevant observation. So for any possible signal realization. So we need to start with not just at time 0 signal and realizations and actions at time 0, but we have to give us a sufficiently long initial period that is exogenous, a sufficiently long initial history that's exogenously given, so that players can use it to determine their behavior in the first period in which the learning algorithm is operating. So after this sufficiently long initial history, in every period, each player I observes their own signal realization, looks back at the past and thinks, oh, which previous situations have I seen in which the signal was the same or similar, then counts for the other player. How often did the other player take this action, that action, and so on? So counts the frequency distribution of the other player's actions and then maximizes expected utility against that. We will look at two specifications of the model, one with finite memory and one with infinite memory. So finite memory, we will interpret as follows. So there are different meanings of finite memory here. I'm not interpreting it as saying there is a finite number of periods back that you remember. You remember at most what happened in the last 5 years. But I will say your memory has limited storage space. So for each signal, you can only sort of store a limited number of past experiences. And if it happens again, then you kick out the longest ago similar experience or identical experience. So it's, and think of it more as a memory limitation that comes from the limited number of cells that you have in your brain. So that's, if there is such a limitation on the number of experiences you can remember, then we call that the finite memory case. If you can always, whenever you see a signal, think back of your complete life experiences in this or similar situations, we call that the infinite memory case. Fictitious play is a learning algorithm that in this language has an infinite memory. Yeah, of course, so, yeah.
Yes, we have another question from D. Feng. Do agents do the inference from histories? This is to say, if I observed his co-player Jay's action histories, then I would think Jay's received signal should be or not be some special lists.
So
I'm not sure.
I'm not sure.
Yeah, maybe.
The question, so in principle players only learn from past experience, that's right. So players are backward looking, adaptive, they are not reflective, they don't think what is really going on here. So maybe we can postpone this, and if that is not an adequate answer, then maybe we can revisit the question after the talk. So this is the process. So the process is a stochastic process because in each period a random signal is drawn. So our statements are going to be properties of the stochastic process. We will denote the random variable that describes which action player I would take in period t if she observed theta I by AIT of theta I. So that's in every period with the model as defined. That's a well-defined random variable. It doesn't matter whether or not you actually observe theta I, that's what you're going to do. But in each period, we can determine it's determined for every signal that a player gets, which action he would take or she would take. And our proposition refers to those, talks about those actions, those random variables. And we have two grandiose propositions. So in principle, we are not aiming for subtlety here. We are not in particular aiming for a result that says, oh, if the game is such and such, the signal distribution is such and such, the similarity distribution is such and such, then you will converge. That's not what we're looking for. We're only looking for the question, if you converge, do you converge to our notion of similarity equilibrium? That's like a consistency check. This can be provide underpinnings for our model. And this is relatively easy in the infinite memory case. So in both cases, so we have to find stochastic formulations. The formulations that I offer may not be completely intuitive, and but there is a little bit limited time to talk about that in detail. So suppose there exists a pair of strategies and a finite time such that with positive probability after that finite time, what players will do forever will be according to this pair of strategies. So it doesn't matter whether that happens with probability 1 or not, but if there is a positive probability event where players' actions, strategies essentially stay constant from that time onwards forever. If players have unbounded memory, then the strategy combination has to be a similarity equilibrium, because by the sort of law of large numbers over time, they've got to figure it out. That's the proof. So proof tries to disguise this with more mathematics. The second case is, how about the case that memory is finite? So we wanted to have that case in particular because our later result, the selection result, will be for the case of finite memory. So this will be a case in which players never really completely necessarily learn what the strategy of the other player is. And so this result is, again, under the assumption of unique best responses, the same assumption that we used when we discussed correlated equilibria. And then there exists a delta such that the following is true. If there is a pair of strategies and a finite time such that after that time, in each period, the probability is at least delta that you play according to this pair of strategies, then the pair of strategies forms a similarity equilibrium. So the difference here is that this condition here does not say some infinite event occurs with positive probability. This condition here said some infinite event occurs with probability. This is a per period event that happens with positive probability. But of course, if it happens in each period after period t with positive probability, it will happen in a long enough block of periods, still with positive probability. And if it, so by some calculation, that's the standard. And then if players' memory is finite, if best responses are unique, that's enough to guarantee that they will learn a similarity equilibrium. A subtlety about this is that there is no assumption in the theorem about the length of the memory. It doesn't say for very long memory. It says whatever your memory is, if this condition is satisfied. But we think that this condition is more likely to be satisfied if your memory is long. But the theorem itself does not require that assumption. So mathematically, the one thing that takes us a while to figure out how to prove is this result, or maybe how to state and then how to prove. This was the second block of this talk. The third block of this talk has to fit into the remaining 3 minutes. As far as I can see, that is, so the third block says, now let's take the learning model with finite memory and let's derive an equilibrium selection result. And this part of the talk will be even more restricted than what I did before, because we will restrict attention to 2x2 games, to play 2 players, 2 strategies each. And actually, no, we will restrict attention to this particular 2x2 game that you see on your screen. Although it doesn't have to be exactly that. Any game with 2 strict Nash equilibria will be fine. We are interested in this particular game. Then we just move on to the very last slide of this talk. So I'm going to skip a few slides. Don't get dizzy if I skip. So there is the last slide. This particular game, 2x2 game, has a famous correlated equilibrium, which I display here on the right-hand side. And as far as I know, this correlated equilibrium showed first up in Aumann's initial paper on correlated equilibrium in 1974. And it has attractive payoffs. It's symmetric and it has attractive payoffs, more attractive payoffs than the mixed strategy symmetric Nash equilibrium of the underlying game. It's a correlated equilibrium that's outside of the convex hull of the set of all Nash equilibria. So for various reasons, it's an example that I use to teach correlated equilibria when I teach game theory. And so what we want to say is we want to ask ourselves, suppose we give players exogenous signal structure that if they recognized it, conditioned on it, they could use it to implement this very attractive equilibrium. Are they going to actually learn it? And we're going to ask this question in the case in which memory is finite. So what is in your memory can always sort of be is a random sample that need not be the true distribution because your memory is finite. And we're going to say, no, under some conditions, players will never achieve this correlated equilibrium, even though the signal structure would allow them to reach it. And that's because their memory is finite and there's always a probability of misleading samples. And this result, so the result will say here, under assumptions 1 and 2, if memory is finite, with probability 1, you will end up either playing the pure strategy equilibrium AA or the pure strategy equilibrium BB. You will never end up playing a correlated equilibrium that is not either of these 2 pure strategy equilibrium. So, but what are assumptions 1 and 2? That's the final gap here. Assumptions 1 and 2 are assumptions on the similarity notions that players use. And essentially, the assumptions say, oh, sufficiently things have to be indirectly similar to each other. So it's not the assumption that everything is similar to everything else, but it's the assumption that for any sort of pair of signals of a player, I can find a chain of similar things that links these 2 signal realizations. That's assumption 2. So it's a connectivity assumption on the similarity notion. And assumption one is a small additional assumption that has sort of the opposite flavor, that makes sure that you can have some experience repeatedly and learn about that experience without interfering immediately over what you do in some other case. So assumptions 1 and 2 are assumptions on essentially on the similarity notion. So on positive probability realizations of signals, and then the similarity notion. Assumption 1 is something that prevents completely synchronized learning, and assumption 2 says similarities notion has to create a sufficiently connected network of signal realizations so that things can spread. The argument here is a contagion argument. The argument is similar, or is related again to the paper by Jakub Steiner and Colin Stewart that I mentioned at the beginning. We have a somewhat different setting, but it's related to that. And I will just pretend that I had reached the final slide just as I planned. I will stop here. Thank you.
Okay, thank you very much for the talk, Tilman. So it's now time that we move to questions from the audience. So if you want to make a question, please state so in the chat, and then we can basically give you pass you the possibility of asking verbally. So any question?
So maybe I'll get everybody started. So at some point during the chat, I was a bit confused that one of the slides at the very beginning, that you had a summary of the results. It was one of the very first slides. And I asked a question, somebody said it's been answered by the slide, but now somebody else pointed out to me, I'm not so sure. So, yeah, it's the one where you have the 3 points. I'm gonna.
Before that,
the slides to remember the question properly. Okay. Yeah. So, so you have this. So you have 2 notions of similarity. You have a notion of similarity in equilibrium, and you have a notion of similarity in learning. And then there is this transitivity and symmetry assumptions that you omit. Mm-hmm. So now it's clear what that does to the equilibrium notion, but it's not so clear to me what that does to the learning process. So in other words, if you assumed symmetry and transitivity, and maybe this is already in the literature, in the learning process, would you converge to correlated equilibrium, which is a symmetric equilibrium with symmetry and transitivity?
So again, so we have 2 sets of results. One set says that if the learning process converges, it converges to equilibrium, and that result does not rely on assumptions on the similarity notion. So it is true also when the similarity notion is transitive and symmetric. And so in that case, the result says, if you converge to correlated equilibrium. Okay. But of course, so the 2 things about that. First, it doesn't give conditions under which you converge, so that is missing. And obviously, that would be much more complicated. And secondly, it just says you converge to some correlated equilibrium. It doesn't say which one. The second, the last result, the equilibrium selection result, I think the connectivity assumption, so assumption 2, makes the, sorry. If I combine that with symmetry and transitivity, I think I'm left with uninteresting cases, because I want signals to be connected indirectly through similarity relations. But if the similarity relation has to be transitive, then anything that's indirectly connected is also directly connected. And that would say that the similarity notion has to be very coarse. so I haven't thought that completely through, but I think the last result on equilibrium selection is only interesting when similarity is at least not transitive.
Okay, thank you. Maybe we could ask Difeng to clarify his question that wasn't clear before, if nobody else has questions.
I have a very, basic question. I understand, that the purpose of this exercise is a first step towards understanding how similarity may shape equilibrium, and in particular in games with asymmetric information. Still, once I see the whole story, the whole exposition that you have made, I wonder whether you have any particular pathological behavior, from the point of view of game theory, that you think that the framework that you have presented today can help us understand or explain.
Yes, the one of the questions in which we are still interested in is the question whether the global game equilibrium selection result will remain true. The global game equilibrium selection result constructs strategies that are highly discontinuous in higher order beliefs. And we wondered whether this result will survive players who learn in this way. So one way of formulating in that game the learning process would be, so if you wanted to learn an equilibrium like that, then so that you receive a real valued signal that could be anywhere on the real line, and your task is to predict will the other player say invest or not invest, conditional on your signal. So you can think of that as conducting a nonlinear, non-parametric regression, right? So you are constructing a function that maps the real line into probabilities, and you don't know what that function is, but it's supposed to be in the equilibrium. It's a step function. You're supposed to discover, can I find the step even if I never see the step exactly. So this was the question. And so at a very early stage, when I had much more time than I have at the moment, I was on sabbatical, I decided to open textbooks on non-parametric regression, pick some algorithms, implement it on my computer, and watch players attempt to learn the global games equilibrium. And sort of through non-parametric regression, I watched them attempt to approach this step function. And so it's not that and so this is the sort of question we have in mind. So there are the famous paradoxes where infinite hierarchies of beliefs matter in great detail. And I wanted to understand whether I can sort of defend that sort of analysis against critique that says, oh, nobody thinks in infinite hierarchies of beliefs, by saying, oh, they don't have to think in it. They act as if they had. Then the question is, can I defend that in a situation where similarity plays a role? So that's the ultimate objective, to ask, can I defend the point of view that players act as if they had infinite hierarchies of beliefs, even though they cannot articulate them? And does that survive this similarity construction? I mean, I don't know whether that answers your question. That's not an empirical paradox that I'm trying to answer. It's more sort of a theoretical paradox that I'm trying to sort out in my head.
No, it makes sense. So we have a question from the audience, from Indrajit Rai. So unmute yourself if you want and formulate your question, Indrajit.
Yes, hi, Tilman.
Hi.
I was wondering, I'm not sure whether I have missed it. Did you talk about uniqueness of the equilibrium? I mean, we know given any correlated distribution, we can have multiple equilibrium problem. Here, for example, given a specific similarity, can you construct a game which has more than one similarity equilibrium?
Yes. The last game was an example because I can just take, if a game has multiple pure strategy Nash equilibria, then one similarity equilibrium will always be to ignore any signal that you get and just play those pure strategy equilibria.
Mm-hmm. No, I guess I'm talking about the other way around. So if you fix take symmetry and transitivity as well, is it possible to? I mean, the very common example is the one you mentioned at the end, the chicken example with 1/3, 1/3, 1/3.
Mm-hmm.
Even that game, even that distribution has another equilibrium, which is just doing the opposite. That is, you play P when you are supposed to play A. So I was thinking if I can think of a similar situation in similarity equilibrium as well. So you have a given similarity, however, when it comes to playing the equilibrium, you may.
So notice, of course, here, because I fix a finite signals structure with a given distribution, I cannot, of course, explore the whole set of correlated equilibria because I just don't have probabilities that are necessarily that are flexible enough. I can only ask if it happens to be that in your life, the noise that you encounter somewhere embedded there is the structure that would allow you to play this correlated equilibrium. Will you pick it up? Now, whether I can construct an example in, say, I think an example in which you would be interested would be an example in which the correlation structure, in which the similarity equilibrium is unique and it's not a Nash equilibrium. I don't know. I haven't, but so in which the only equilibrium that you can play conditional on what you see is a correlated equilibrium. That's not a Nash equilibrium. That would be an interesting example. I mean, in general, I should say I'm working on this. I have become over the years interested in the question: how can players learn to play a correlated equilibrium? And here, in principle, I've constructed a setting in which we make it easy for players to learn a correlated equilibrium because we just give them exogenous signals, and all that you have to figure out is how to condition on them. So the difficulty, of course, is that it may be embedded in a large amount of noise, and you might not sort of discover the right way of conditioning. There is another literature on convergence of learning to correlated equilibrium. So the literature on regret-free learning, where players, the result says that players perform an even more complicated task because there are no exogenous signals in that. So the correlation is generated by players simultaneously moving from one pair of action to another pair of action. So it's a history average that creates the correlation. In a sense, I think of that as the more ambitious way of learning a correlated equilibrium because it's not by conditioning on exogenous things, but it's sort of the conditioning on your endogenous history that leads you to correlation. So at some point I decided, and as I have already hinted, I like to program my computer to watch simulations. I programmed a regret-free learning algorithm for chicken and tried to watch my players learn the correlated equilibrium of chicken, or one of the attractive correlated equilibria of chicken. My players on my computer always fail. So the regret-free learning algorithm result says you, in the long run, you approach the set of correlated equilibria. That's the theorem in heart and muscular. And the players that I observed, yes, they did approach this correlated equilibrium. They approached very directly a pure strategy Nash equilibrium. And so in my mind, it's still an open question. Can I find a sort of an interesting model that players actually learn, say, the attractive or also, as you mentioned, the unattractive correlated equilibrium of chicken? And I don't know.
Thank you. Thank you.
So thank you. So it's already 15 past 6. So at this point, we are going to stop the recording, and the official part of the seminar finishes. So we will remain a few minutes, but that's basically all for today. We hope to see you next week. And